Good morning, students of grade 9. Today we are going to start our new chapter about equilibrium of a body. First of all, we are going to talk about the equilibrium of a body under the action of two forces. When a solid is in equilibrium, the two forces acting on this solid should have the same line of action, opposite directions, and the same magnitude. For an example, in the first picture in here, a car was at rest on a road. The two forces acting on the car are the normal reaction of support vertically upward and the weight force vertically downward. At equilibrium, the vector relation between those two forces is that the weight vector plus the normal vector is equal to zero vector, which means that the weight vector is equal to minus normal vector. As a magnitude, the weight force and the normal force are equal to each other. In the second example, a ball is suspended to a rope connected to a wall. The two forces acting on the ball are the tension force and the weight force. Both forces are opposite in direction and having the same line of action. For this body to be at equilibrium, both forces must have equal magnitude. The condition of equilibrium, or the vector relation applied between the two forces acting on the ball, is that the weight vector plus the tension vector is equal to zero vector, which means that the weight vector is equal to minus tension vector. As a magnitude, the weight is equal to the tension force. Now, we are going to talk about the principle of interaction. The principle of interaction states that if an object A exerts on an object B a force Fa over B, which means the force done by the ball A on ball B or by the body A on body B, the body B will exert on A reaction force, which is the force done by the body B on body A, such that both forces have the same line of action, as shown in the following figure. Both forces have the same line of action, which is horizontal. Both forces have opposite direction. The force done by A on B is to the right, while the force done by B on A is to the left. Both forces have opposite directions, and both forces have equal magnitude. We say that an interaction has taken place between A and B. Hooke's law. Consider a box of mass m connected to the free end of a spring of stiffness constant K as shown in the adjacent figure. The box is at equilibrium under the action of two forces, the weight force and the tension force. L0 represents the length of the spring when it's unloaded, while L represents the length of the spring when we suspend a mass m from the free end of the spring. The increase in the length between the two cases is called the elongation of the spring. Its symbol is x or delta L. It's calculated using the formula delta L is equal to L, the new length of the spring, minus L0, the initial length of the spring. Since x represents a distance, its SI unit is meter. Hooke's law states that the tension T in the spring is proportional to the corresponding elongation delta L, which is also equal to x. The expression of Hooke's law is that the tension force is equal to the stiffness constant K of the spring, which is expressed in Newton per meter in SI unit, times the elongation delta L, which is expressed in meter in SI unit. The tension force is expressed in Newton. To convert from Newton per centimeter into Newton per meter, we must multiply by 100. And to convert from meter into centimeter, we must multiply by 100. This pyramid allows us to evaluate the different forms of the expression of Hooke's law. First one, tension force is equal to the stiffness constant K times the elongation x, or the stiffness constant K is equal to the tension force divided by the elongation x, or the elongation x is equal to the tension force divided by the stiffness constant K of the spring. Now we are going to talk about the elongation curve of the spring. The elongation curve of the spring is the curve of the tension force as function of its elongation x. As shown in the adjacent figure, this curve shows the variation of the tension force in Newton as function of its elongation x in centimeter. As we noticed from the following curve, the curve of a perfectly elastic spring is an increasing straight line passing through the origin, which verifies Hooke's law. The equation of the straight line is in the form of t equal k times x, which is similar to the equation of a linear straight line y equal ax. The slope of the line is the stiffness constant of the spring, where k, the stiffness constant, is equal to the slope, which is equal to t2 minus t1 divided by x2 minus x1. We took two values from the curve, 2, 2 and 0, 0. We must be noted that the elongation x must be converted from centimeter into meter by dividing this number 2 by 100, so that the slope, which is equal to the stiffness constant, will be 2 minus 0 divided by 0.02 minus 0, which gives us that the stiffness constant of the spring is equal to 100 Newton per meter, which is the SI unit of the stiffness constant. Now we are going to talk about an important remark. Given a spring and a box and a ball M connected to the free end of the spring, the forces acting on the ball is the weight force and the tension force. At equilibrium, W vector plus tension vector is equal to 0 vector, which means that the weight vector is equal to minus tension vector. As a magnitude, the weight force is equal to the tension force. If we write the formulas of the weight and the tension forces, we'll have a relation between the mass, the gravity, the stiffness constant K, and the elongation x. This relation is that mass times gravity, which is the rule of the weight, is equal to the stiffness constant K times the elongation x, which is Hooke's law's rule, the rule of the tension force. Finally, we are going to solve a simple example about Hooke's law. Given an S is a solid of mass 300 gram, given that the gravitational acceleration g is equal to 10 Newton per kilogram, and the stiffness constant of the spring is equal to 2 Newton per centimeter. The solid S is suspended from the free end of the spring as shown in the adjacent document. The solid S is in equilibrium under the action of its weight, W vector of magnitude W, and another force. The first question. Give the name of the other force exerted on S. The box S is at equilibrium under the action of two forces. The first one is the weight force, which is vertically downward, and the second one is the tension force, which is vertically upward. So, the other force acting on the box is the tension T of the spring. Specify the vector relation between the two forces exerted on S. The vector relation between the two forces exerted on S is the condition of equilibrium of S, which is the T vector plus W vector is equal to 0 vector. Calculate the value of each of these two forces. First, to calculate the value of the forces tension and weight, we must look at the given. We have the mass and the gravity, which allows us to find the magnitude of the weight force. Using the formula of the weight, weight is equal to mass times gravity. The mass must be converted from gram into kilogram by dividing 300 by 1000. The mass will be equal to 0.3 and the gravity is 10, the weight will be 3 Newton. Since the body is at equilibrium and both forces must be equal in magnitude, so T vector is equal to minus W vector, as in magnitude T force, the tension force, and the weight force are equal, so that the tension force is equal to 3 Newton. Finally, calculate the elongation delta L of the spring. To find the elongation delta L of the spring, we must apply Hooke's law. Hooke's law states that the tension is equal to the stiffness constant K times the elongation delta L. So, delta L will be equal to the tension force divided by the stiffness constant K. Tension force is calculated in part 3, which is equal to 3 Newton, and the stiffness constant K is given in the which is equal to 2 Newton per centimeter. Since the stiffness constant is in Newton per centimeter, so the elongation delta L will be in centimeter. By calculation, delta L will be equal to 1.5 centimeter.